Hello again and welcome back. And again, this is Joe Reinhardt, your instructor for the Cisco CCNP route training from TrainSignal. In this particular lesson, we're actually going to dig into EIGRP. We looked a little bit at design. Now we're going to get into the fundamentals of the protocol, how it operates, and then specifically how we're going to configure it in our lab. So just as a roadmap for our lesson, we're going to start off with the mechanics of the protocol. It's important to understand the piece parts and how things function in order to be able to really show excellence as a network engineer. So we'll look at protocol mechanics. We'll look at the various tables used by EIGRP. We're going to dive into EIGRP metric calculations. For those of you that are not fond of math, buckle up. This is going to be intense. Then we'll look at how to configure the basic lab exercises in the EIGRP pod of our lab. And then finally, we're going to go through a process of verifying that everything is operating within the specifications that we've already looked at. So to begin with, it's important to understand the building blocks of how EIGRP functions as a protocol. And in order to do that, we're going to take three principles and we're going to flesh them out a little bit. We're going to look first at EIGRP neighbor relationships because it's particularly important. We're going to look at the types of packets that are used in EIGRP operations. And then we're going to look at an overview of the topology exchange process. To begin with, one of the things that makes EIGRP very distinct and sometimes referred to as a hybrid protocol is because it has elements of distance vector routing and it has elements of link state routing, which is why it's called a hybrid protocol. Distance vector protocols, for example, do not have formal neighbor relationships, and link state protocols do, and that's one of the reasons why EIGRP kind of sits in the middle between the two protocols, because EIGRP establishes formal neighbor relationships, very much like OSPF does. And there's a couple rules about how that needs to operate. First, these devices, as pictured to the left, have to be directly connected. They can't be removed by several networks or interfaces. Direct connection is important. There needs to be peering on the primary subnets, meaning that you can put primary IP addresses on an interface and a number of secondary ones. It has to be established on the primary subnet. You can't have the primary subnet of, let's say, 192.168.1.0 on one interface, and then on the neighbor interface have it be 192.168.1.0 as a secondary address. It'll never establish a peering relationship that way. Another thing, and we'll actually dive into this a little bit later, the K values that make up the EIGRP metric have to match. In addition, one of the things about EIGRP is that when you start the routing process, you specify an autonomous system number, and those numbers have to match for peering to take place. And finally, if you have EIGRP neighbor authentication, which we'll do later, those strings have to match as well. If any of those things are not, if any or all of those things are not true, the neighbor relationship will not be established and route exchange will not happen. Another thing with EIGRP neighbor relationships is, like some of the other link state protocols, EIGRP uses hello messages, which establish the relationship and also act as a keep alive and maintain. These are multicast to IP address 224.0.0.10. You'll notice that that's in the Class D multicast space. But it's an important one to remember because all of EIGRP's operations take place on the 224.0.0.10 address. There's other ones for OSPF and some of the other protocols, but it's important to remember that as well. And also, unlike OSPF, there's a single peering relationship between all routers on multi-access networks. For instance, if all the routers, let's say 5 routers, are on an Ethernet segment, there's going to be a relationship for each one of those routers with the other routers. There's no concept of a designated or backup designated router in EIGRP. These hello messages that we talked about for discovery and maintenance are sent at regular intervals on all configured interfaces, and we'll demonstrate what that means here in a little bit. On high-speed interfaces, fast Ethernet, Ethernet, and so forth, it's going to be sent out every 5 seconds. For lower speed interfaces, which is generally considered serial interfaces, frame relay, and so forth, it's going to be sent out every 60 seconds. And these are actually adjustable, but those are the defaults. Another thing in neighbor relationships is something called the hold time. Hold time is actually a function of what we talked about with the hello protocol acting as a keep alive. 3 times whatever the hello interval is, which we just looked at, would be the amount of time that the EIGRP neighbor will consider the neighbor still alive. In other words, one of those can be missed, two of those can be missed, but if the third interval is missed, then there's a problem. So just doing 3 times the hello interval, it's 15 seconds on high-speed interfaces and 180 seconds on low-speed interfaces. We want to now look a little bit at packet types. There are distinctive packet types that are used in all EIGRP operations, and it's interesting to note that these are IP protocol number 88. There is no TCP or UDP used in the operations of EIGRP. It's a distinct protocol type of its own. It uses something called the Reliable Transport Protocol, or RTP, to transmit data to neighbors using multicast in most cases and in some cases unicast. Now, the acronym RTP is also used for Real-Time Transport Protocol, which is used in voice, but they're in no way related other than the fact that they happen to have the same acronym. So you can see these packet types are actually pictured out to the left. There's hello, update, query, reply, ACK or acknowledge, and then goodbye. Each has a specific function. Some will be sent reliably, some will not. But these are all important in operations. Hello is used in neighbor discovery and maintenance. We talked about that. Update is when routing information is being sent between neighbors. Query is when there's a process where one neighbor wants to be able to ask if other neighbors know about a specific route. That's a query packet. Reply, obviously, there's a response to that. Acknowledgement is used at very different intervals for something that need to be acknowledged. In other words, if something's been transmitted, an acknowledgement sent back. And goodbye is an interesting one because it's a packet that basically does sort of a quiet and graceful shutdown. Sometimes when you're looking at the command line, you'll see EIGRP sort of doing these things. But these are the different packet types, and they all are quite regularly used in the protocol. So a neighbor relationship's been established, everything's up and functioning, then there's a topology exchange process. So when the neighbor first comes up, it establishes the relationship, and then it begins to send things out to the neighbors. In other words, it starts with the hello packets. We talked about that. It's an initial discovery. It's a keep alive mechanism, and this is also critically important. The hello intervals do not need to match on neighboring routers. The neighbor will actually adjust its hello intervals to that of the neighbors, so they can be variously configured. For instance, if you adjust the timers because you want convergence to happen a little bit faster, then that's one of the things that will happen. It'll automatically jump. OSPF we'll look at later is not that way at all. It's much more finicky. Now, one of the things is, as far as the hello packets being sent out, there's a couple of exceptions. First of all, if you don't have the network command configured to identify a particular interface, it won't send or receive any hello packets on the multicast address of 224.0.0.10. If you use the passive interface configuration under the router configuration mode, it will not send any hello packets out that interface. And if you use static neighbor configurations, it's very seldom done, but if you statically configure your neighbors, then it will not send the hellos out because it will just be depending on the static configuration. So keep that in mind. So the three process for the neighbor stages, it starts up with neighbor discovery and adjacency, establishing the relationship. Then it will send full routing topology updates. It will send everything out that it knows in its topology database, shares it with the neighbor, and then once that happens, it's actually a very quiet process where only updates are sent, status changes only. One of the things that this gives the advantage of with EIGRP is there's a great deal of bandwidth conservation because there's not a lot of unnecessary traffic. And route calculation happens between neighbors. It's not all the way through an area where packets are flooded much as they are in OSPF. Another important aspect of understanding the fundamentals and building blocks of EIGRP as a protocol is knowing the tables that the protocol uses to do all of its operations. And there are three primary ones. There's the neighbor table, there's the topology table, and then of course there's the IP routing table. And we'll examine each one of these. To begin with, one of the tables that you need to keep in mind is the neighbor table. It is the list of fully adjacent, full relationship, between EIGRP neighbors. And the table, you can actually see it on the router by doing the show IP EIGRP neighbors command, and it'll actually create a table very much the one like the picture to the left. And then you can see there are a number of different aspects of this particular table, and you want to understand what each one of those means. First, the address is the IP address of the neighbor. Obviously, the neighbor, the peering relationship, and all those sorts of things. That's the way it can be identified. Interface is the interface from the local router that's used to reach that particular neighbor. You notice here there are two entries that use the same interface, and that's because it's a multi-access network, in this case a multi-point interface. This is from router 1 that we have in our lab. Hold is the hold time. This again is the 3 times the hello interval that actually looks at when a neighbor is still considered alive, and after that obviously it's flushed from the neighbor table. Uptime shows the length of the relationship, how long it's been up and functioning. If the neighbor relationship resets, then this would obviously go back to 0. The SRTT is the smooth round trip time, and this is one of the things that's used to understand how long it's taking to receive an acknowledgement from something that's set out. This is one way you can look and actually see if perhaps there's congestion in the networks that's causing issues. RTO is the retransmission timeout, how long to wait for an acknowledgement before again sending things out. And then the queue count is actually the packets that are in queue waiting. You can see that there are 0 in this particular aspect of the neighbor table that we have transmitted. But these are some of the things to look at and understand in terms of relationships between EIGRP neighbors. One of the most important tables that's used in EIGRP is the topology table. It's actually a list of all EIGRP routes that were either learned locally, because they're connected, or from updates, in other words, from neighbors coming in update packets. You can display the EIGRP topology table by the show IP EIGRP topology command. And this is obviously just done from exec mode in a particular router or layer 3 switch. So it's important also to understand what these particular acronyms mean. You can see that it's sort of listed at the top, but I want to do a little bit more deep diving on this. So P stands for passive. Passive means that a network is available and it's usable in the routing table. It's not in an active calculation process. A is actually active, which is the opposite. The EIGRP route is currently in a query, reply, or route calculation process. It's not available for use yet. U is update. It means the network is being updated. Obviously goes without saying. Query is that a network query request has been sent out and this particular device is awaiting the response. R is reply, which means that the router is sending a reply or awaiting an acknowledgement. And then S is the SIA status, which means that the query has not been acknowledged. It can indicate a convergence problem. There is a condition called stuck in active, which means that the route never stops being calculated because a process of query and reply has been interrupted. The reply has been lost, the packet's been discarded, or something's happened, and it can create a stuck in active, which can actually cause neighbor relationships problems as well. So this is just sort of a snapshot of the topology table. You can see that it also lists feasible distance and reported distance, which we'll talk more about later. The final table in EIGRP that's of critical importance is obviously the IP routing table. The IP routing table is populated with routes from the EIGRP topology table. That's how the table is seated. And when you do specifically execute the show IP route EIGRP, it will display just the EIGRP routes, not connected and things of that nature, but everything that's a part of the EIGRP process and installed in the routing table. And just a little bit of a roadmap here. D is the designation for EIGRP routes. E is not. E1, E2 are something that are displayed when you're dealing with OSPF. But it's an EIGRP internal route, meaning it's internal to the routing protocol. It's been defined as through some connected network or through the network statement. And it has an administrative distance of 90, which is the lowest among the regular routing protocols, with the exception of external BGP. EX, as you can see down toward the bottom, is a EIGRP external route. It's been learned through redistribution. It has an administrative distance of 170. In this particular case, it's a default route that's displayed. The next thing you'll see in the IP routing table is the 90/ and then you can see these large numbers, such as the cases at the top. This is the administrative distance of the route, as we just talked about for D routes. And then the other is the feasible distance of the route, which we'll dive into a little bit more in route calculation a little bit later. But that's something to keep in mind, making sure these things match. And then VIA just shows the source of the routing update, the next top address, typically the neighbor router. So a snapshot of the IP routing table. EIGRP metric calculations That's the next section we're going to actually take an examination of, because the EIGRP metric numbers can look rather random at first glance. We're going to actually dive into how it's all put together. We'll start with the metric weights, or the K values, which you mentioned a little bit earlier. We will step through the metric calculation process, the mathematical aspects of the algorithm. And then finally, we'll look a little bit at the EIGRP route selection, or dual diffusing update methodology for route selection. To begin with, EIGRP metric calculations begin with the metric weights, or they're sometimes called the K values. Displayed to the left is the actual output from one of our routers. It happens to be router 1. And each one of these K values I've broken out using a color code, which may be a little comical because I'm actually partially colorblind. But I happen to know that they matched in this particular case. But there are 5 K values that are used in metric calculation. And when you execute the show IP protocols command for EIGRP, it will actually display what the K values are and how they're set up. So K1 is bandwidth. Bandwidth, sometimes referred to as constrained bandwidth or smallest bandwidth. It's actually the smallest bandwidth factor along the route to a particular subnet or network. So if it's 100 megabits all the way and there's one segment that's 64K, it's the 64K that'll be calculated because it's the smallest bandwidth along the path. And at first glance, you may look at that and go, that makes no sense whatsoever, and why not look at everything all the way through? But if you think about, if you're driving on a highway, no matter how big the highway is, if there's construction going on and there's been an accident and that particular highway is down to 1 or 2 lanes, it vastly affects how the traffic goes through. Whereas just the fact that it's an 8-lane highway all the way through, that constraint is actually the reason why you wouldn't want to select that particular route, unless, of course, you enjoy sitting in traffic for hours. So constrained bandwidth is typically just referred to as bandwidth. K2 is load, expressed in an integer between 1 and 255. And again, doing the show interface command, which is what's pictured to the left, you can see that the load here is 1 out of 255, which means it's not really loaded at all. It's the lowest setting that you can have. But obviously, the more load there is in an interface, and these are usually calculated in 5-minute segments, that kind of gives you an idea of what it looks like. Delay, now this isn't constrained delay, but this is actually cumulative delay from the point of origin, that particular router, to the destination network. And again, that's looked at in tens of microseconds. In other words, you look here and it says it's 100 microseconds. So actually, when you do route calculation, you have to move the decimal over 1. K4 is reliability. Again, this is the reliability interface. Notice here it's 255 over 255. And this is how reliable that interface is. If it's up and down and flapping, obviously that's going to affect the reliability factor. And then there's MTU, or maximum transmission unit, the minimum one that's being used along the way. Now, ironically, this is identified in a lot of the literature as saying it's a part of the route calculation, but it actually never has been at any time. So it's part of the K values, but it's basically irrelevant. So it's important to understand which of these K values EIGRP uses by default, and it actually only uses bandwidth, constrained bandwidth, and delay. So K1 and K3 are the only ones that are actually actively used in route calculation. Now notice here, if you did the show IP protocols command, it would show K1 is 1, K2 is 0, K3 is 1, because remember K3 is delayed, 4 and 5 are also 0. So those all have to match between neighbors for a neighbor relationship to form. If you want to change them, for instance, if you wanted to just take into account bandwidth, you could change it using the metric weights command under the EIGRP process. But these K values are actually important to understand so you know how the pieces fit together in the protocol. The other thing we want to look at, now that we've understood K values and knowing that constrained bandwidth and cumulative delay are the basic default parts of the metric, we want to actually look and see how that can be calculated. And looking out here to the left, we actually have a picture of the connections between router 1 and router 3. And we're actually, of the two of those, looking at the VLAN 12 link here. So 10.3.3.3/32 is the loopback interface of R3. And the bandwidth between them is, in this case, 100 megabit. And the delay is 5100 microseconds. So here, to understand, when you actually look at the output and the calculation of the metric, it can get confusing. For instance, look here. Now, we'll distinguish between FD and RD later, but FD is actually what you'll usually see in the routing table. The metric's actually showing as 156160. When you look at the 100,000 and the 5100, the bandwidth and delay, it can look really confusing and not make any sense at all. So we're going to dive into that in actually the next slide. But it's important to understand that metrics for EIGRP are always expressed in integer format. There are no decimals, there are no fractions. It's just simply rounded up to the next whole number. And in this particular case, because the higher bandwidth is more preferred, this is what's being used as the primary route between R1 and R3. Now there is an additional path that exists over to the left on the frame relay network. We'll talk a little bit about that later. But the calculation here is looking at the bandwidth and delay between R1 and R3 and an actual formula that we're going to look at in just a moment. So this is a little bit as to what the background is before we look at the specific calculation. And the 156160 is actually the number that we'd be looking at. So one of the things that I did to make this a little more understandable, at least from my perspective, is to be able to look at the mathematical part of how the EIGRP metric is calculated. Now you can see, as we'd already talked about in the previous slide, the value is 156160, and I wanted to try to understand how it all came together. So the way that this is calculated is pictured here to the left. Now it says metric, this is the EIGRP metric, 10 to the 7th power divided by the least bandwidth. Remember, this is constrained bandwidth along the way. In this case, it's 10 to the 7th power divided by 100,000. Then add in the cumulative delay. And remember that it's tens of microseconds, so that's why underneath there where it says delay, it's only 510, because it's in increments of 10, so we had to move the decimal place over. So 100,000 into 10 to the 7th power, then adding in the 510 for the delay, then taking those two together and multiplying it by 256 is where this number comes from. And so when I created the calculator, I actually made it possible to put in whatever the bandwidth input is up in the left hand under input, the delay underneath, and then it actually showed how it came up with the EIGRP metric there using that particular formula. So if you ever really need to figure out the mechanics of why a particular metric is being calculated, you can put it together in an Excel spreadsheet with almost no effort, and that can actually be very helpful knowing what the math is. So using this calculator, figured out that the metric, how it all matched together, again came up with the value of 156160, as well as looking at the output of the routing table. And these metric values that are calculated by this formula are what you see in the EIGRP topology and IP routing tables. And you do show IP route, it'll display it there, administrative distance, then the metric, and it'll also, under the words FD, will actually display it in the EIGRP topology table. So once EIGRP has done the route calculation, what the best metric is, then there's a process that's used for actually selecting and installing that, not only as the best route in the topology table, but then ultimately the IP routing table. And EIGRP calculates two values. This is very, very critical to understand. Two values when selecting the best route to a particular destination subnet. The terms are feasible distance and reported distance. Now once EIGRP has gone through the process of calculating the metric, then there's a process it uses for taking a particular route and not only putting it in the topology table, but installing it as the IP routing in the IP routing table as the best available route. This process is critically important to understand because it drives everything else that goes on with EIGRP. There are two values that EIGRP uses to make that determination and to be able to determine what constitutes a loop-free route. The terms are feasible distance, usually FD is the acronym used, and this is the metric of the best route to a subnet as calculated locally on a router. For instance, in this particular case, look to the left. The diagram R1, the feasible distance from R1 to 10.333/32, the feasible distance, that's FD, is the 156160. That is how R1 calculates how to get to that route. The next term that's also important is reported distance, and incidentally, sometimes you will hear reported distance described as advertised distance. It means the same thing. But reported distance is the metric of the best route to a subnet as calculated by the next hop or upstream neighbor. In this case, R3. 10333/32 lives on R3, and R3 is reporting what the best metric is to that particular network. So feasible distance, R1's viewpoint of the network. Reported distance is R3's view of the network. If the subnet was actually several routers up, it would still be the next hop router that's talking about what its perspective is to be able to reach that particular route. So feasible distance and reported distance. In this particular case, you see that the feasible distance, 1033/32, from R1 is 156.160. It's essentially whatever the reported distance. Notice it says 128.256. It's that plus whatever R1's cost is to reach R3. So you put those two together and you end up getting the feasible distance. So 156.160 and 128.256 are the feasible distance and reported distance in calculating the EIGRP metrics. So once the reported distance and the feasible distance have been calculated, and the reason why it's important to begin with is because EIGRP uses those two particular data points to determine whether or not the route is loop-free and thus usable. And it's a mathematical state called the feasible condition. And the feasible condition is actually pretty easy to understand. If the reported distance, remember this is the route metric from the perspective of the next hop router, if the reported distance is less than the feasible distance, and the feasible distance is how that particular local router computes the metric to that route, if the reported distance is less than the feasible distance, then the feasible condition is considered true. It's usable, it's loop-free, and it can be placed in the IP routing table as well as the topology table. So it's called the feasible condition. So you can see here, just looking at the math, you have the feasible distance to 10333 as 156.160 and the reported distance of 128.256. So is the reported distance less than the feasible distance? Well, 128.256 is less than 156.160. Therefore, it's a usable route. Therefore, it passes the feasible condition, and therefore, it is usable. So that's one of the ways, in fact, the way that EIGRP determines the route to install in the IP routing table. Now, another aspect of this is the way EIGRP refers to routes. You'll notice here there are two terms in our diagram up here to the left. There's successor, which is in blue, and feasible successor, which is in black. Now notice the successor, this is using the interface we've been talking about, the Fast Ethernet VLAN 12 interface, and the feasible successor is the frame relay interface. So the routes that are chosen by the diffusing update algorithm are referred to using these two terms. The successor is the best route to a subnet that's installed in the routing table. Now, if there were multiple VLAN interfaces, there would be multiple successors. Successor is just the term for the valid route that's in the topology table and the IP routing table, the best route that's available. But one of the things that's very distinct about EIGRP is this concept of a feasible successor. This is a route still meeting the feasible condition, it's still loop-free, but it's immediately usable upon failure of the successor. So if there's an outage on the VLAN 12 interface or on either one of the physical interfaces, the route in the frame relay network, the feasible successor, is immediately placed in service. There's no route recalculation, there's no shortest path first algorithm, it's immediately installed. And that's one of the things that's very distinctive about EIGRP, is it uses this, essentially this backup route, this route held in reserve, and it's immediately usable. I actually designed an entire backup routing solution for a very large retail customer just a few years ago that took this whole concept into account because they were using EIGRP. It meant then that if there was an outage on their primary circuit, this other was immediately available. They didn't have to do anything. It was all automatic. So understanding this and the distinctive aspect of EIGRP, the successor and feasible successor, and understanding this whole feasible condition math. It's very simple, but knowing that is essential to understanding how EIGRP operates as a protocol and also in a network. So feasible condition, successor, feasible successor. What if there's a situation where the valid route, the successor route, fails and there isn't another one available? There isn't this feasible successor, this backup route, this loop-free route. What happens next? How does EIGRP decide what's next? Well, it uses dual, the diffusing update algorithm, which is essentially distributed to the point of the local router, and it uses that to calculate a new route. It sends a query. Remember we talked about the packet types in EIGRP. It sends a query regarding that particular route to all the directly connected neighbors. So in this case, if you remember our lab, R1 has a direct connection to R3 using 2 links, R4 using frame relay, and R2 using frame relay. If both of these routes went away, the feasible successor and the successor to 10333, it would then query R4 and R2 using a query packet, and then asking if it knows about a route in its table that's an alternative to get to that. Now, if R3 fails as a neighbor, it'll also be deleted from the neighbor table. While the route is being calculated, it's referred to as going active. If you remember when we looked at the topology table, P meant passive, it meant it was in steady state. A for active means that a query and reply process is going on to calculate the best path to a particular network. When the new successor is selected, all the route calculation has been done, the route then returns back to passive status. So that's the simple process that EIGRP uses to be able to determine a route when a successor has failed and there is no feasible successor. So now that we've been able to peel back the layers of how EIGRP operates as a protocol and sort of gotten the basics out of the way, now we can actually apply it to a real-world environment, well, to some degree, by looking at how we are going to be able to apply this in the lab that we've set up. So what we're going to do is we're going to look a little bit at the configuration commands we're going to be using. We're going to be looking at the devices that we have in our EIGRP routing domain. And then finally, we're going to actually configure the devices. So first, let's just look a little bit at from an overview standpoint of how we're going to be able to configure these. What commands are we going to use? Pictured here to the left is R1, R2, R3, R4, and R5. The lab ASA is going to be out of scope. It's already configured. But we're actually going to configure EIGRP across all of these devices. So it starts with the creation of the EIGRP routing process, which is just router, EIGRP, and the autonomous system number. Remember, it has to match on all devices. You can't have 1 on one device and 15 on another and expect them to peer. Now you can sort of create sort of a pseudo multiple area thing mimicking OSPF, but you'd still have to have multiple EIGRP routing processes. Another thing that's going to be important is to make sure the no auto summary command is executed under the EIGRP routing process. Otherwise, as we talked about earlier, it will act like a classful protocol, which is kind of defeating the whole purpose of using variable length subnet masking and so forth. So those are some things that we'll need to do right away to get the process started. Then, in order for the topology table to be populated, it has to be seeded from 2 sources. Network and subnets on interfaces local to the router using the network subcommand. Remember, network, then identifying the way that particular interface is valid on the router using, IP addressing and masks and so forth. So things. Another way that its topology table is seeded is from other networks through the redistribute command. Now, redistribution is going to be a later lesson. After we've gone through OSPF and after we've implemented BGP, then we're going to be able to distribute all 3 protocols into one another selectively with some filtering in order to be able to create full reachability. But those are the 2 primary ways that the EIGRP topology table and ultimately IP routing table is populated. So another thing we're going to do is we're going to make sure that we have the bandwidth commands added to the serial interfaces so that the correct metric is calculated. If you remember, serial interfaces by default are put at the bandwidth of 1544 T1, and we're just, for the purposes of the lab exercises, are going to be using 128-bit links through here. So we're going to have to actually go to the specific interfaces, and we're going to have to put that as part of the calculation process. Another thing we're going to do is we're going to manually configure the router ID EIGRP typically chooses the highest loopback as the router ID, and since we've only got one loopback on our routers, that'll happen automatically, but it's really important to be able to specify it because duplicate router IDs actually can create problems. If, for instance, there were no loopback addresses, then EIGRP would just simply pick the highest address on a valid functioning interface. But it's best practice to actually manually and statically configure it. It's the IP EIGRP router ID command that we'll be putting in there. Another thing we'd like to do is, because the interface bandwidth on the serial interfaces is so small, we want to actually adjust a little bit what that will be. So the default is 50% of the configured bandwidth, which again is another reason why you want to make sure you define it correctly. If these serial interfaces are assumed to be T1 and it's only 128K, then it's going to use 768K, and that's way more than the actual bandwidth of the interface. So we'll adjust it using the IP bandwidth percent EIGRP subcommand on the interfaces as part of the basic lab exercises. So let's review just really quickly what we're going to be using as far as device types in the lab for EIGRP. We have 5 routers pictured here, R1 through R5. R1 is going to have a multi-point and a point-to-point frame relay subinterface topology. This is going to give us an idea of how EIGRP acts differently on these types of interface. And then there's also a redundant link to R3, which is going to be over VLAN 12, which obviously will be the preferred route because of the better bandwidth. On router 2, we're going to have a point-to-point frame relay subinterface matching the one on R1. There's going to be a VLAN connection to R5, and you can see that we'll be doing EIGRP stub configuration in the advanced part of our lessons. Router 3 we've already covered. Router 4 will be supplying a default route to the rest of the network, which we'll configure. Router 5 will have a stub configuration, and ASA 5505 is actually going to be creating our connection to the internet, but we will not be doing any configuration on that device. It'll already be pre-configured. So just for purposes of our lab exercises, we're going to be specifying autonomous system number 100 on all our routers. We're going to use loopback 0 as the router ID. We're going to disable automatic summarization. And then I wanted to take a moment to explain how we're going to configure the bandwidth on the serial interfaces. On our multi-point subinterfaces, it's best practice to be able to take the least bandwidth on the links and multiply it by the number of links. Now, if they're all 128K, that makes it easy, but if one was 128K and one was 64K, it'd make more sense to be able to take the 64K one and multiply it across the interfaces for conservation purposes. But we're actually going to use 256 because that's the bandwidth times the number of links in the multi-point group. And then on each one of the spoke routers, we're actually going to use 128K because from their perspective as spoke routers, that's the way it'll be. And we're going to limit the serial interface bandwidth consumption of 45% use by EIGRP. So now we're actually going to configure the parts of our lab for EIGRP as we've already looked at. What you see in front of you on the notepad section of the screen is actually something that's a particularly good practice. If you want to be able to quickly configure devices, it's best to write them out in something like Notepad and then just paste them in. So I just wanted to be able to show this as an easy way to be able to handle that particular aspect. But let's start with router 1. Do show IP protocols just to get an idea of what is running, and there's nothing running. Configure terminal. Router EIGRP 100. Remember, we wanted to do no auto summary because you don't want automatic summarization. Now we want to do EIGRP router ID 10111. Now we actually want to be able to put EIGRP on all active interfaces. So let's do a do. The do command is actually allows you to be able to process exec commands from within a configuration. So we'll do show IP interface brief. So we can actually see what we want to be able to do. Now, one of the options you have in EIGRP is just to be able to use major network numbers. So we're just going to make this easy. So we'll do network 10.0.0.0, then network 172.16.0.0, and then because these are Class C addresses, we have to put them in one at a time. 192.168.10, 11.0, and then 13.0. So to make sure this is working the way we want it to, we can do show EIGRP interfaces. And it is running on all the interfaces we want it to. So that is working the way we planned. So now let's go to router 2. On this one, we'll do another, let's just do that first, show IP interface. Okay, configure terminal, router EIGRP 100. We'll do this with the wildcard mask. So we have 10.2.2.2, and we want to be able to just say only that address. Now we can do network 172. Let's do 192.168, and let's supernet this 00. You do 0.0.255.255. And then we can do network 172.16.12.0, 0.0.0.255. Now you'll notice back on here, it's showing the neighbor relationship up between R1 and R2. So if we do show IP EIGRP neighbors, voila, there we go. Router 3, let's just make things really, really easy. Configure terminal. Router EIGRP 100, no auto summary, and then let's just do the catch-all command, and it should bring everything up. So we should have two neighbor relationships between R3 and R1. Show IP EIGRP interfaces. And there we go, show IP EIGRP neighbors. And there's two neighbor relationships like we would have expected. One of the things I want to be able to do is make sure that the, oh yes, because notice in here I forgot to put the no auto summary command. Router EIGRP 100, no auto summary. R4. Router EIGRP 100, network 172.16.0.0, we'll just make that one easy. Network 192.168.4.0, 0.0.0.255, do 44.0, and then network 10.4.4.4, 0.0.0. And do show IP EIGRP interfaces. And it's running on all the interfaces we want it to. Show IP EIGRP neighbors. And voila! Because it's a multi-point interface, we have two neighbors. And then finally R5, this one will be, again, also very easy. Configure terminal. Router EIGRP 100. No auto summary. And we'll just use the catch-all on this one too. Show IP EIGRP interfaces. Four, excuse me, and then show, and there we go, our neighbor relationship. Now if we go back to R1, show IP EIGRP interfaces, neighbors. Show IP route EIGRP. And there we go, we've got a very impressive routing table. So let's just go ahead and do the bandwidth configuration we talked about. So we'll do interface serial 00/12, which is the point-to-point interface. Bandwidth, we said we were going to do 128K. And then we want to do the bandwidth percent. EIGRP 100, and we wanted to do 45. And that's essentially the entire process. We'll do the multi-point interface just for the sake of completeness. Serial 00-134, bandwidth 256, and IP bandwidth %EIGRP 145. That's essentially all of what we'd be looking at in terms of the basic configuration. And if you recall our discussion, we talked about feasible distance. There's the administrative distance. That's the feasible distance of this particular route. We could do show EIGRP topology table. Feasible distance and reported distance, just like we talked about. Now notice here, there's one successor. This is the route to R3, as we talked about before. This is the primary route that we've been looking at all this time and calculating everything for. But this is the frame relay route right here. This is the feasible successor. So in this particular case, just like in a few of these others, if the successor went away, feasible successor, which isn't listed in the routing table right now, would take over. And that's pretty much all there is to the basic configuration of our lab environment. Now to wrap up our lesson, we're actually going to look at a little bit about the verification process. Now keep in mind we already did some of this as we were configuring the lab, but this kind of gives you an idea of what the processes should look like. We want to make sure that the basic configuration was functioning, which we did. We want to be able to verify functional neighbor relationships. In this case, we actually saw the neighbors come up and did a listing on R1, so everything appeared to be in order. But then there's also a split horizon issue, which we didn't address, that we're going to go back and take a look at. So first, to be able to verify basic EIGRP operation, making sure it's up and running, the show IP protocols command, which is pictured to the left, is helpful. Now notice it actually lists the K values, and as you would expect, K1 and K3 have a 1, which means count them in the metric, and the rest are all set to 0. This helps you verify the process is running. It also gives you a good idea of what networks EIGRP is propagating, what interfaces it's running on, as you can actually see there. Another thing is to be able to confirm EIGRP is operating on the interfaces, and this is the show IP EIGRP interfaces command, which we executed. Make sure the interfaces you've identified and are expecting are actually appearing there. You'll also be able to see the autonomous system number displayed, and that can be a good helpful point. And then it should show the number of peers that are listed for that particular interface on the show IP EIGRP interfaces output. To the left here, you can actually see neighbor relationships using the show IP EIGRP neighbors command, which we also used. You should see the correct interface displayed, that it's being sending and receiving hellos on, that the correct IP address or addresses are displayed, and I wanted to explain the statement statistics are non-zero. The different statistics like RTO and others should actually have numbers other than 0. Q count I wouldn't worry about, but a lot of these other things, if they're showing zeros, that might indicate there's a problem. And make sure you can use ping and trace commands to confirm connectivity is active. Can you get to all the routes that are displayed in the routing table, as well as neighbors, especially neighbors? That's important. And also display your routing table and make sure, for instance, all the loopbacks are propagating, and in the table that the LAN interfaces, VLAN interfaces, serial interfaces, all are being displayed and are all reachable. So let's look a little bit at this split horizon issue. In this particular case, there are going to be missing networks in the IP routing table. All the networks in R1, because it's the primary router, it's showing everything. R3, some networks like those from R4 are not being included because that's a part of the multi-point interface problem. And on R4, not all the networks are being advertised as well. And the solution here is actually to use the split horizon command. Now keep in mind there is a no IP split horizon, but it needs to be EIGRP split horizon and put on the multi-point interface. Router 1, which is where the problem would be, and we'll do show running configuration. And here's the culprit. IP split horizon is enabled by default, so it is not going to display here. So what we want to do right now, configure terminal, interface serial 00.134. This is only in the case of multi-point interfaces. Point-to-point interfaces are treated like point-to-point links. So I'm going to do no split horizon, IP split horizon, EIGRP 100. Once you do this, you'll notice the neighbor relationship is going to drop. IP EIGRP interfaces, and I actually didn't drop. I was expecting it to. Oh, you'll notice here I mistyped it. This is one reason why it's very important to be able to verify what it is you're typing. So first we'll do no IP EIGRP 110. No router EIGRP 10. Now we'll go back to our interface here. We'll actually put it in correctly. And as I promised, the neighbor relationships dropped because the split horizon had changed. So the first neighbor came back up and the others come back up. So now show IP EIGRP neighbors. Now let's go to R3 and see if those routes are coming through the way they're supposed to. Show IP route. Let's do show IP route EIGRP and make it simpler. Let's go to R4 and take a look. R4 also serves as our terminal server, so logging into it's a little bit different. Show IP route EIGRP. And see, there's a lot missing still. Actually, that relationship just came back up. Let's take a look at R4. Go back to R1. Route. Make sure it's correctly identified under the interface. And it's got that correct. Now you see that R4 is actually getting the table, whereas before it only this many entries. Now it's listing things out the way it's supposed to. And that's a good example of the things that can happen with split horizon. You can end up losing routes and things not going the way that you expected. So just some key terms. RTP is Reliable Transport Protocol. This is the data transmission protocol that EIGRP uses to guarantee ordered delivery. K-values, which are also called metric weights. This is the different components that are used to calculate metrics in EIGRP. The hold time, again, this is expressed as a multiplier of 3 times the hello interval. It says how long the neighbor should wait before it considers that particular neighbor dead. Feasible distance is the EIGRP metric to a destination network from the perspective of that router. Reported distance is the EIGRP metric to a destination as reported by the next hop router, or the directly connected neighbor. The feasible condition is the test of a valid loop-free route, and it's simply that the reported distance must be less than the feasible distance. Successor is the term used for a valid primary EIGRP route to a given destination network or subnet. And the feasible successor, this is the backup route held in reserve that we talked about, the secondary route to a destination network and usable immediately. So we covered a lot of material. Let's just summarize. We went over protocol mechanics down into the nitty-gritty details. We went over the tables used in EIGRP. We looked at how EIGRP calculates the metrics. We went through and configured our basic lab exercises, and we verified how everything's working. Thank you very much for your kind attention. I know we covered a lot of material in great detail. but it's important and foundational to the rest of what we're going to be using later. Thank you for your kind attention, and we look forward to talking to you again soon.